In this question, we're working in R3, but we have this inner product that's not our usual dot product. So it's this formula here where we do the transpose of V times the matrix times the vector W. And we're given this basis, 1, 1, 1, negative 1, 0, 1, 1, negative 6, 1. And our first step is to verify that this is orthogonal given that inner product. So notice that it's not orthogonal with our usual dot product. The third vector is actually not orthogonal to the first one. And once we have established that this is an orthogonal basis, it should allow us to express this V pretty easily using the same sort of theory that we've used in the previous sections of this unit. So we are going to kind of take for granted that this operation here is an inner product without verifying that. And we're going to go ahead and do our inner products between the vectors here. So the first thing we'll do is verify. So I'm going to do this. Step 1. So we will just follow the rule as it's described. So the 1, 1, 1 with negative 1, 0, 1. So I'm going to do the transpose. So 1, 1, 1 and times this matrix. And then times negative 1, 0, 1. So I'll clean up that product on the right. So I should get negative 1, 0, and 1. And then when I multiply those things out, yeah, I get 0. So yes, it is in the 1 by 1 matrix or the 1 by 1 vector. But the number part that we're looking at is the 0, and that looks good. So I'll do the next pair, 1, 1, 1 with 1, negative 6, 1. We're also going to kind of, take it for granted that when we do this, it should be commutative, but that is kind of a property of the way the transpose is set up and the fact that that's a symmetric matrix. So that hopefully is a little easier for you to believe. So I'll set this one up. 1, negative 6, and 1. And so now when I do this one, I will get 3, negative 6, and 3. And yeah, so I'm going to get 0 there. Good. And then finally, the last one, I'll do this pair, negative 1, 0, 1 with 1, negative 6, 1. And this calculation on the right, I've already done, so I'll just rewrite it. But you can see again that when we multiply those two things, we do get 0. So all of them are 0, so it is an orthogonal basis, and that is what we're going for. Okay, so now on to the second part of the problem, expressing V as a linear combination of the basis vector. So we're just going to do same thing that we've done before. Because we know that the basis is orthogonal, we can just do this as a bunch of projections. So V is going to be the projection of V onto, I guess, this first vector, V1, plus the projection of V onto V2, plus the projection of V onto V3. And it's going to be kind of this chaotic expression here. But yeah, so I'm going to get my V, which is just ABC, onto 1, 1, 1. Plus ABC onto negative 1, 0, 1. Plus ABC onto the 1, negative 6, 1. And I'm gonna skip a little step in these computations and do the product of the matrix times W first. And so what we'll get is the transpose ABC, and then the 1, 1, 1 product is going to be 3, 1, 3, and then 1, 1, 1, 3, 1, 3. And then the next one is going to look pretty similar, except we need the negative 1, 0, 1, and that product times the middle matrix is going to be actually the same thing, negative 1, 0, 1. And then plus, again, my transpose, and the 1, negative 6, 1, we actually did already compute that one. It's right here, 3, negative 6, and 3. And that's 1, negative 6, and 1. And we can work these out. So this will be 3a plus b plus 3c over 7 times 1, 1, 1 plus c minus a over 2 times negative 1, 0, 1, and then plus 3a minus 6b plus 3c over, and that should work out to 42 times the last one. And I'm not going to double check it, but you can actually go through and work out that if you expand and simplify and do all that, it actually ends up being exactly the ABC vector. So hopefully that checks out, but that should be it.